When you look up at the night sky, the moon appears as a silent, unchanging sentinel. Its cratered face, locked in a permanent gaze with our planet, gives the illusion of a geologically dead world. It looks like a cosmic museum where the footprints of Apollo astronauts sit entirely undisturbed in the vacuum of space. But beneath that still, gray dust, a violent and dynamic geological drama is unfolding. The moon is not a dead rock. It is a living, shrinking, and quaking world. Welcome to G Fun Facts Online, where today we are diving deep into the fascinating field of lunar seismology, a branch of planetary science that has profoundly shifted our understanding of our nearest celestial neighbor. Through a combination of half-century-old data, cutting-edge orbital imagery, and advanced modern computing, scientists have discovered that the moon's interior is actively cooling and contracting. As it shrinks, its brittle crust buckles and cracks, triggering moonquakes powerful enough to pose serious hazards to future human exploration. To truly understand the shrinking moon, we must first look back to the Apollo era. When astronauts first walked on the lunar surface, they were venturing onto a world whose interior was a complete mystery. Was it solid all the way through? Did it have a molten core? Did it experience tectonic activity anything like what we see on Earth? To answer these questions, Apollo 11 astronaut Buzz Aldrin deployed the first lunar seismometer in 1969, powered by 2 panels of solar cells. This instrument was the vanguard of the Apollo Passive Seismic Network, which eventually became a series of advanced sensors placed by the crews of Apollo 11, 12, 14, 15, and 16. The later stations were equipped with radioactive thermal generators. This incredible piece of engineering allowed them to survive the brutal 2-week-long lunar nights, where temperatures plummet to unimaginable extremes. Because of this power source, they could transmit continuous data back to Earth until the network was officially decommissioned in 1977. For 8 years, these delicate instruments listened to the heartbeat of the moon. What they recorded shocked planetary scientists. The moon was vibrating with activity. Initially, researchers parsing the data by hand with pen and paper identified around 13,000 seismic events. Imagine the sheer dedication required to sift through endless reams of paper data just to spot the subtle wiggles of a moonquake. Decades later, with the help of modern algorithms and artificial intelligence, scientists like Keisuke Onodera from the University of Tokyo reanalyzed the Apollo short-period seismic data and uncovered 22,000 previously overlooked moonquakes. By studying how seismic waves travel through the lunar interior, scientists were able to classify moonquakes into 4 distinct categories. The first category is deep moonquakes. These are the most common type of lunar seismic event. Deep moonquakes originate between 701, 200 kilometers below the surface, which is about halfway to the moon's center. Interestingly, these are not caused by the moon's own internal heat, but rather by the Earth. Just as the moon's gravity pulls on Earth's oceans to create our daily tides, Earth's massive gravitational field constantly stretches and squeezes the moon. This immense tidal stress causes deep, rhythmic fractures within the lunar interior. Deep moonquakes often occur in concentrated nests and peak in frequency depending on the moon's orbital position relative to Earth. The second category involves meteoroid impacts. Because the moon lacks a thick atmosphere to burn up incoming space debris, it acts as a giant acoustic detector for the entire solar system. Everything that hits it makes it ring. The Apollo seismometers recorded more than 1,700 impacts from meteoroids striking the lunar surface, sending violent shockwaves rippling through the crust. The third category is thermal moonquakes. The lunar surface experiences some of the most extreme temperature swings in the solar system. It plunges to -250 degrees Fahrenheit or -150 degrees Celsius during the long lunar night, and then bakes at 250 degrees Fahrenheit or 120 degrees Celsius under the harsh daytime sun. This rapid, intense heating and cooling causes the lunar crust and the loose surface rock, known as regolith, to physically expand and contract. These microscopic movements generate thousands of tiny, shallow tremors every single lunar morning and evening. Finally, we have the fourth category, shallow moonquakes. While deep and thermal moonquakes are relatively weak, shallow moonquakes are the true monsters of the lunar underworld. Originating within the top 200 kilometers of the crust, these tectonic events are incredibly powerful. Out of the original catalog of seismic events, 28 were identified as shallow moonquakes, registering up to a staggering 5.5 on the Richter scale. Now, on Earth, a 5.5 magnitude earthquake is enough to damage buildings and cause significant alarm. But on the Moon, the effects are vastly more dramatic due to the unique nature of lunar geology. This brings us to a phenomenon known as the ringing bell effect, which explains exactly why moonquakes are so exceptionally destructive. If you experience a magnitude 5.5 earthquake on Earth, the intense shaking usually lasts for only a few seconds to maybe a minute. The Earth's crust is fractured into large tectonic plates, heavily saturated with water, and highly weathered by wind and rain over billions of years. These features act like a giant geological sponge. When an earthquake happens, the wet, fragmented crust rapidly absorbs and dampens the seismic energy, stopping the vibrations relatively quickly. The Moon, however, is completely different. It is bone-dry, highly fractured from billions of years of violent asteroid impacts, and relatively cold in its upper layers. When a shallow moonquake strikes, the seismic waves do not dissipate. There is no water or soft rock to absorb the energy. Instead, the seismic waves bounce around continuously within the brittle, fractured crust. Scientists famously describe the Moon as ringing like a bell. Lunar seismic energy can take anywhere from half an hour to several hours to completely dissipate, with the most intense, violent shaking lasting for over 10 minutes. Imagine that for a moment. 10 minutes of non-stop, intense shaking. For a human outpost or a fragile spacecraft resting on the lunar surface, 10 to 30 minutes of continuous, high-amplitude shaking is an absolutely catastrophic hazard. It would test the limits of any engineering we currently send into space. But what exactly is causing these powerful shallow moonquakes if the Moon completely lacks moving tectonic plates like we have on Earth? The answer lies in the slow, inevitable, and global cooling of the lunar core. This is the science of the shrinking Moon. To understand the origin of shallow moonquakes, scientists had to look at the Moon on a global, planetary scale. The Moon formed approximately 4.5 billion years ago in a chaotic environment of intense cosmic bombardment and radioactive decay. This violent birth left the Moon as a molten, glowing sphere of magma. Over billions of years, the Moon has been slowly radiating that primordial heat out into the freezing vacuum of space. As the Moon's deep interior cools, it physically contracts. To visualize this dramatic process, scientists often use the analogy of a grape drying into a raisin. As the fleshy, moist interior of the grape shrinks, the outer skin must buckle, fold, and wrinkle to accommodate the reduced volume. The Moon undergoes the exact same process. However, unlike the flexible skin of a grape, the Moon's outer crust is incredibly rigid, solid, and brittle. As the volume of the Moon's interior steadily decreases, the solid crust is forced to compress. It gets pushed together tighter and tighter until, eventually, the stress becomes too great, and the crust violently breaks. This breaking forms what geologists call thrust faults, where one section of the lunar crust is pushed violently up and over an adjacent section. These geological fractures manifest on the surface as cliff-like stairsteps, known as lobate scarps. Scientists estimate that over the last several hundred million years, which is just a blink of an eye in geological time, this contraction has caused the Moon to shrink by about 150 feet or 50 meters in diameter. For a long time, researchers believed these lobate scarps were just ancient relics of the Moon's distant, active past. They thought the Moon had been quiet for billions of years. That assumption completely changed with the launch of NASA's Lunar Reconnaissance Orbiter, or LRO. Equipped with the incredibly powerful Lunar Reconnaissance Orbiter camera, the LRO has mapped the lunar surface in unprecedented, breathtaking high resolution. The images beamed back to Earth reveal the vast, global network of thousands of relatively small, completely pristine thrust faults. The visual evidence was absolutely striking. These lobate scarps looked remarkably young. They cross-cut small impact craters that would have otherwise been erased by the slow, continuous churn of micrometeoroid impacts if they were ancient. Furthermore, they featured bright, unweathered regolith, which strongly suggests recent geological movement exposing fresh rock. The definitive proof came when Dr. Thomas Waters, a senior scientist emeritus at the Smithsonian's National Air and Space Museum, combined the new LRO imagery with the old Apollo seismic data. By using a highly specialized algorithm designed to mathematically relocate the epicenters of the shallow moonquakes recorded back in the 1970s, Waters and his brilliant team discovered a smoking gun. The epicenters of the strongest shallow moonquakes perfectly aligned with the young lobate scarps mapped by the LRO. Furthermore, many of these destructive quakes occurred when the Moon was at apogee, which is its farthest point from Earth in its elliptical orbit. This is a specific time when Earth's tidal stress is added to the Moon's internal global contraction stress, making fault slips highly likely. The conclusion was undeniable. The lobate scarps are not ancient fossils. They are highly active fault lines. The Moon is actively shrinking today, and the scraping, thrusting crust is the exact engine driving the powerful, shallow moonquakes. Further expanding on this incredible revelation, recent research by Cole Napavier and Tom Waters mapped another class of tectonic features known as small mare ridges. While lobate scarps were mostly found in the lighter, heavily cratered lunar highlands, over 100 previously unrecognized small mare ridges were identified in the dark, flat basaltic plains of the lunar Maria. These ridges share an average age of about 100 to 120 million years with the lobate scarps. This proves beyond a shadow of a doubt that the entire global surface of the Moon, from the towering highlands to the flat Maria, is buckling under the immense pressure of its shrinking interior. This massive paradigm shift in lunar geology has arrived at a very critical moment in human history. NASA's incredibly ambitious Artemis program aims to return humans to the Moon for the first time since 1972, with the ultimate long-term goal of establishing a permanent, sustainable human presence. Unlike the Apollo missions, which landed in the relatively flat, safe, equatorial regions of the Moon, Artemis targets the treacherous lunar South Pole. This specific region is of immense strategic value because its deep, permanently shadowed craters act as literal cold traps, harboring billions of years' worth of ancient frozen water ice. This ice is the gold of the space age. It can be mined and purified to provide drinking water, separated into breathable oxygen, and even processed into liquid hydrogen and oxygen to be used as rocket fuel for missions to Mars and beyond. However, this quest for lunar water brings astronauts directly into a massive seismic danger zone. By meticulously mapping the lunar South Pole, researchers have discovered a dense, dangerous cluster of lobate scarps, crisscrossing the very areas NASA has selected as prime candidate landing sites for the Artemis 3 crewed mission. For example, the Degurlache Rim 2, a highly sought-after candidate landing region, contains a young thrust fault scarp that advanced orbital models suggest is highly active right now. In fact, the epicenter of one of the most violent shallow moonquakes ever recorded by the Apollo network was relocated to within just 60 kilometers of the lunar South Pole, encompassing several proposed Artemis landing zones. The hazard waiting for our astronauts here is twofold. First is the direct, physical threat of the moonquake itself. As we discussed, a magnitude 5.5 quake lasting for hours could severely damage rigid lunar habitats, critically crack the concrete-like foundations of launch pads, or disrupt highly sensitive, life-saving, life-support machinery. As Renee Weber, a planetary scientist at NASA's Marshall Space Flight Center notes, understanding this seismic hazard is absolutely vital to the survival of future lunar outposts. The second, and perhaps even more terrifying hazard, is the threat of landslides. The lunar South Pole is defined by its incredibly rugged, extreme topography, with massive craters like Shackleton featuring plunging, steep slopes. The surface of these dangerous slopes is covered in regolith, which is a loose, dry, highly frictionless layer of fractured rock and microscopic dust. Computer models evaluating the slope stability in the South Polar region have yielded truly alarming results. Even light to moderate seismic shaking from a distant lobate scarp slip could be more than enough to completely destabilize the regolith on these steep crater walls. If an astronaut, a delicate lunar rover, or a multi-million-dollar mining habitat were positioned inside one of the permanently shadowed regions when a shallow moonquake strikes, they could be easily buried by a silent, cascading avalanche of lunar dust and rock. Dr. Waters warns that scientists hope to sound a cautionary note that the moon is a seismically active body and that there is a potential, serious hazard to long-term settlements if they are located too close to a young fault. Future mission planners must now completely change their mindset. They must treat the moon not just as an exploration destination, but as a highly active seismic construction site. Structural engineering for lunar habitats will require radically new designs, including flexible foundations, massive shock absorbers, and rigorous hazard zoning to ensure that critical infrastructure isn't built directly atop an active thrust fault. Despite the incredible discoveries derived from the legacy Apollo network and the modern Lunar Reconnaissance Orbiter, our current seismic map of the moon is still woefully incomplete. The Apollo seismometers were entirely localized to the near-side equatorial region of the moon. Because of this, we have virtually zero direct seismic data from the mysterious lunar far side or the extreme, frozen polar regions. To safely establish a permanent lunar economy and ensure the safety of future generations of explorers, an entirely new era of lunar seismology is dawning. NASA and various international space agencies are actively developing next-generation instruments to deploy a massive, global lunar geophysical network. One of the most highly anticipated missions on the horizon is the Farside Seismic Suite, or FSS. Scheduled to fly on a commercial lunar lander, the FSS will make history by placing the very first highly sensitive broadband and short-period seismometers on the far side of the moon. Protected from the brutal extreme temperature swings by advanced thermal shielding, these sophisticated instruments will easily survive the deep freeze of the lunar night and peek deep into the moon's hidden core. This will finally help scientists map the global distribution of tectonic stress. Furthermore, future Artemis astronauts will likely be tasked with deploying vast, interconnected arrays of modern seismic sensors all across the rugged South Pole. These new, high-tech networks will meticulously monitor the subtle thermal cracking of the regolith, listen closely for the distant thud of meteoroid impacts, and serve as an incredibly vital early warning system for the violent shifting of the shrinking lunar crust. For thousands of years, humanity has looked at the glowing orb of the moon and seen a comforting symbol of quiet permanence. Today, thanks to the persistent, brilliant curiosity of planetary seismologists, we know the true story. Our moon is a dynamic, contracting world, literally groaning and fracturing under the immense weight of its own cooling heart. As we actively prepare to leave our footprints in the lunar dust once again, we do so with a newfound, profound respect for the restless ground beneath our boots. Exploring the moon in the 21st century will not just be a matter of conquering the harsh vacuum of space, but mastering the violent tremors of a shrinking world. Thank you for listening to G Fun Facts Online, where we bring the wonders of the universe directly to you.